So in this video we're going to find the locations of horizontal and vertical tangent lines for a polar equation. So the polar equation that we're interested in is r equals 2 sine theta. The graph of it is down here, and just inspecting the graph we're expecting to find horizontal tangent lines here and here, and we're expecting to find vertical tangent lines here and here. That's the worst vertical line I've drawn today, I think. So I draw another one that's just as bad. Third time may or may not be a charm. So we're looking for two verticals and two horizontals just by graphically inspecting things. And the idea is we need to know when we're going to need to calculate the derivative, dy dx. And in the previous video we saw that we could calculate dy dx by taking the polar equation and parameterizing it. So if we do that, we know that x as a function of theta is equal to r times the cosine of theta. And we know we can replace r with the 2 sine theta, so x equals 2 sine theta cosine theta. And this is actually a trig identity. 2 sine theta cosine theta is the same as 2 times the sine of 2 theta. So there's parameterized x. This is x as a function of theta. And then we can parameterize y. We can parameterize the y coordinate for this polar equation. We know that y equals r times the sine of theta, but r is the same as 2 sine theta, so we replace r sine theta with r sine theta times the sine theta that we already have. It's going to equal 2 times the sine squared of theta. So now we have parameterized x and parameterized y coordinates for our polar equation r equals 2 sine theta. So we know that if we have a set of parametric functions, we can calculate dy dx by taking the derivative with respect to the parameter, so d theta of the y parameterization, so d theta of 2 sine squared theta in the numerator, 2 sine squared theta, divided by d theta of the x parameterization, which is 2 times the sine of 2 theta. So the derivative of 2 sine squared, we need to take the derivative of the squaring function, so the 2 will come down, we'll get 4 times the sine of theta. And then we need to use the chain rule, so we need to take the derivative of the inside function, so the derivative of sine is cosine, and this is going to be over. And then the derivative of this is going to be 2 times the cosine of 2 theta, because the derivative of the sine is the cosine. And then the chain rule says take the derivative of the inside function, so the derivative of 2 theta is just 2. And things can simplify a little bit. 4 is the same as 2 times 2, and 2 sine theta cosine theta is the trig identity that is equal to sine of 2 theta. So we can get one of these 2's to cancel, then 2 sine theta cosine theta gives us the sine of twice theta over, and in the denominator we have the cosine of 2 theta, and the 1/2 we can factor it out front if we want to. So the idea here is that the horizontal tangent lines will occur when the derivative is equal to 0. And the only way for the derivative to be equal to 0 is for the numerator to equal 0. So we want to know when is the sine of 2 theta equal to 0. And then we would take the sine inverse of both sides. So twice theta equals the sine inverse of 0. And we can always put plus 2 pi k if we want to identify that there's infinitely many solutions. We're not going to need to do that for this particular equation, but we could. And then we want to recognize that the sine inverse of 0 is just 0. and then we would divide both sides by 2, which would just give us that theta equals 0. So remember, this is a polar equation. So if theta is equal to 0, we're saying, hey, we want an angle of 0 with respect to that polar axis, which is right here. So that means don't rotate at all off the polar axis. And then we could find the radius that goes with it. So here we know what the radius is. So polar coordinate would be find the radius. So r equals 2 times the sine of theta, but theta is equal to 0, and the sine of theta is 0. So 0 times 2 is 0. We get a radius of 0. So we wind up with the ordered pair, r theta, equaling radius is 0, angle 0, which is going to correspond to the pole or the origin. Here's the point 0, 0 in polar form. Notice that doesn't get us this up here. And the reason it doesn't get us is we need to remember that the solutions to the sine inverse function always comes in pairs. They come in supplementary pairs. The two angles that you get have to add up to 180 degrees or pi radians. So to get the other angle when you get to this step right here, the way that we get the other angle that goes with it is we go twice theta equals pi, or 180 degrees, minus the sine inverse of 0. That's to give us the supplement of this angle. We need the supplement. We need the angle and the angle supplement. Those are the two answers. Remember, they have to add up to 180 degrees or pi radians. So if you take pi minus sine inverse plus sine inverse, you get pi. So 180 degrees. And then we can continue to solve this. This is going to be, sine inverse is going to be 0, so this is just going to be pi. So we get this, and then that means that theta is going to equal, divide both sides by 2. We get pi over 2. And indeed, if you look at this horizontal tangent line, it looks like you need to rotate pi over 2 radians to get that quadrantal angle. And then we just need the radius that goes with it. So we plug our pi over 2 into the radius equation. We get radius equals 2 times the sine of pi over 2. But the sine of pi over 2 is 1, so 2 times 1 equals 2. So we get the polar coordinate, radius 2, comma, angle pi over 2, which corresponds exactly to this point right here. Rotate through pi over 2 degrees from the positive x-axis or the polar axis, and that gives you the, and position yourself with a radius of 2 or a distance of 2 from the origin. So this is the ordered pair right here, 2 comma pi over 2. So the other two angles will come from, the other two angles are going to come from setting the cosine of 2 theta equal to 0. We want to know when is the denominator undefined, because that's when we get the vertical, horizontal, the vertical tangent lines. The only time a 0 down here wouldn't give us a vertical tangent line is if we had something, for example, like a 0 up here, and we had an indeterminate form causing a sharp point in the graph. So the next step is to set the denominator of the derivative dy dx equal to 0. So we get cosine of 2 theta equals 0. And we go through the same game. We go twice theta equals the cosine. We take the cosine inverse of both sides. So cosine inverse of 0. And then we remember that the inverse cosine function has, the cosine function has even symmetry. So when we take the cosine inverse of both sides to get the two solutions, it's a different process than it is for the sine. For the sine function, we get supplementary pairs. For the cosine function, we take advantage of the even symmetry of the cosine function, and we say, hey, we're going to get plus or minus some angle. And then we do want to remember there are infinitely many answers, so we could go plus 2 pi k if we needed to. So twice theta is going to equal plus or minus, the cosine inverse of 0 is just pi over 2. So plus or minus pi over 2 plus 2 pi k. And then we multiply both sides by a half. That's going to give us theta equals plus or minus pi over 4 plus 1/2 of 2 pi k is just going to give us a pi times k. So we're adjusting for the period of the function that gets adjusted for in this process. So we're going to get two angles out of this. So we'll do the easy one first, the plus pi over 4. So when theta equals pi over 4, and if we look over here at this vertical tangent line, it visually looks like this angle should be pi over 4 or 45 degrees. I wonder where my face is. Hopefully not blocking things. So it looks like it's the correct angle, and then we just need to get the radius to go with it. So the radius is going to equal 2 sine of pi over 4 equals, let's stretch it out this way, equals 2 times the sine of pi over 4 is root 2 over 2. So we just get the square root of 2. So this point located right here, where the vertical tangent line is radius. Radius is the square root of 2. And the angle is pi over 4, because these are polar coordinates. So we do radius followed by angle. Now the other one initially doesn't look promising, so we want to. It's the more difficult one. So we'll think about it two different ways. So theta equals negative pi over 4. Let's run with that. So initially this doesn't look right, because negative pi over 4 would have us rotating down 45 degrees into quadrant 4. So the angle that we get looks wrong. It looks like it's actually the reflection of the angle we want through the origin. So we get the negative pi over 4 degree angle right there. But if you calculate the radius here, it's actually not going, things are going to be okay. The radius equals 2 times the sine of negative pi over 4. So this would equal 2 times, well, the sine of negative pi over 4, because we're in quadrant 4 here, is going to be negative root 2 over 2. So we'd actually get the opposite of the square root of 2. So what's happening is we're rotating down, we're rotating the wrong way, and then but the negation on the radius actually would bounce us over here. So it would be legit. There'd be nothing wrong with saying the ordered pair right here is a radius of negative pi over 2 and an angle of negative pi over 4. This is probably not be standard or preferred, but it wouldn't be incorrect. Rotate the wrong way, that puts you at a radius of square root of 2, but then reflect that root 2 through the origin into the position that you want. So it would be correct. The other way that we could think about this, so there is another way to think about it, and it's to use the fact that we get infinitely many solutions. So if we're thinking about the minus pi over 4, we could also look at it this way. Theta equals, we get negative pi over 4, but it is plus pi k. And remember, k is just any integer you wish. So if we looked at the case where k was equal to 1, we would get 1 times pi, get a common denominator, 4 over 4, and we add this up, we actually would get negative pi over 4 plus 4 pi over 4 is 3 pi over 4, which is exactly the angle that we would get. Here's 1 pi over 4, 2 pi over 4, 3 pi over 4 running out into that position. So we could use an angle of 3 pi over 4. If we take advantage of the fact that we can go plus 2 pi k to represent all possible solutions, just rotate it into the position you need. Now when you go up here and do your radius calculation, you're going to get radius equals 2 times the sine of 3 pi over 4, but the sine of positive 3 pi over 4 in quadrant 2 is just root 2 over 2, so we just get the square root of 2. And so we could also put this as the square root of 2, and this angle here as 3 pi over 4 would be legit. Remember in video 1 we identified that a polar coordinate isn't unique. There's infinitely many points, or infinitely ways, to represent a point using polar coordinates. So it's going to be most common to use the angle between 0 and 2 pi, but you don't have to use that angle between 0 and 2 pi.